Hi everyone, this is Mrs. G.A. and today we're going to learn about end behavior and other characteristics of function graphs. So before we start, I have a quick warm-up for you guys. So please pause the video and see if you can find the slope between these 2 points. And I have a little hint right here for you. We'll check your answer in just a few seconds. All right, so go ahead and check. So this was a review of using the slope formula, which is right here. It's y2 minus y1 over x2 minus x1, which gives you the change in y, so that's the rise, over the change in x, which is run. So I label my coordinates accordingly, and I substitute these values into the formula. So for the first one, you should end up with 3 over 6, which simplifies to 1 over 2. And for the second one, you should get 3 over negative 1, which is negative 3. Do be careful here whenever you're subtracting a negative. Remember, subtracting a negative is actually like adding. So just make sure you're careful with your parentheses. Okay, so first we're going to talk about how to describe the end behavior of a graph. So the end behavior of a graph describes what happens to f of x, which is the y values, as the x values get very, very, very large or very, very, very small, so towards the ends of the graph. So there's two sides that you need to be able to describe. First, you describe what happens when the x values are increasing infinitely. So if your x values are increasing infinitely, if you think of an xy axis like this, when your x values are increasing infinitely, it's essentially saying to the right. So you're trying to describe what's happening way, 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 way off to the right of your graph. So we do this with a very specific notation. We read it as x approaches positive infinity, f of x approaches blank. And here's how we write it. We say as x approaches positive infinity, comma, f of x approaches, and then you say what your graph approaches. So sometimes your graph will be going up forever, sometimes your graph will be going down, and sometimes your graph will actually approach a number. So this is essentially saying when I move to the right, my graph is heading towards this value. Then you need to describe what happens as your x values are decreasing infinitely, which on the x-axis, the negative numbers are to the left. So you're describing what's happening to the left. So the notation is very similar, but this time we say as x approaches negative infinity, f of x approaches blank. So again, this is what's happening moving towards the right, and this is what's happening moving towards the left. Okay, so let's try a couple of these together. We're going to describe the end behavior of all three graphs. So let's look at graph A. So here we have a linear function. So let's start with the end behavior to the right. So if you look at the graph, you can see that it's just heading up and up and up. And if we add that arrow, it implies that it is going to be going up forever. So we can say as x approaches positive infinity, again, that's moving towards the right, my y values are going to go up infinitely. So we would say f of x approaches positive infinity. So this is a way of saying moving to the right, my graph is going to go up forever. Now let's look at what's happening on the left side of our graph. So same thing, we have a graph that's just going to keep continuing in that direction, except this time it's going down. So this time we can write as x approaches negative infinity, f of x approaches negative infinity. So this is a way of saying moving to the left, my graph is going down. So that's the end behavior for graph A. Now let's look at graph B. So here we have a quadratic equation, we have a parabola. So again, let's start with what's happening moving to the right. So as we move to the right, look at what's happening. My pointer is just going to keep going up and up and up forever. So we would say as x approaches positive infinity, f of x approaches positive infinity. Again, moving to the right, my graph goes up. Now let's look at what happens on the left. So if you trace your graph going to the left, you can see that our graph is also going to go up infinitely. So we would say as x approaches negative infinity, f of x approaches positive infinity. So again, moving to the left, my graph is going up. So both end behaviors are going up. Now let's look at graph C. So here, again, starting on the right, let's trace. As I move towards the right, you can see that our graph is going to go up infinitely. So we would say as x approaches positive infinity, f of x approaches positive infinity. Now, if we look towards the left, we start tracing towards the left, you'll see that our graph is actually approaching a number. It's not going up forever, it's not going down forever. It's actually getting closer and closer and closer to 0. So here's a case where it's approaching a value instead of infinity or negative infinity. So here we can say as x approaches negative infinity, f of x, the y value, approaches 0. So you can see moving to the left, my graph is getting closer and closer to 0. All right, so go ahead and pause the video here and see if you can give these two a try, and then we will check your answers in just a few moments. Okay, let's have a look. So for the first graph, you can see that moving towards the right, our graph is going down. So as x approaches positive infinity, f of x approaches negative infinity. And then moving towards the left, our graph is going up. So as x approaches negative infinity, moving towards the left, f of x approaches positive infinity. Our graph goes up. For graph B, you can see that when I'm moving to the right, my graph goes down, and when I'm moving to the left, my graph goes down. So here you can notice that our end behavior is the same. So as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, moving to the left, f of x also approaches negative infinity. And I do want to point out, sometimes you'll see for positive infinity that we'll actually add the plus sign in front. So some people add the plus sign every time, some people don't for positive infinity, so it is optional. Okay, so now we're going to move on to talking about a few different defining characteristics of functions. So we're going to learn how to describe where a graph is increasing and decreasing, where the minimums and maximums are. We're going to learn how to find the average rate of change between 2 points, and we're going to learn how to find the zeros. So let's start with increasing and decreasing. So increasing, it's pretty intuitive. If you're reading your graph from left to right, like you would read a book, a graph is considered increasing if your graph is going up. So if you look down here, if I start tracing my graph from here to here, my pointer is moving up. So in this region, I am increasing. For decreasing, again, you're still reading your graph from left to right. It's whenever your graph is going down. So if I continue on, you'll notice after I pass -1, my pointer is going down. So in this region, we can say our graph is decreasing. If I keep tracing, now all of a sudden my graph is going up again. So we have another region that is increasing. So we're going to learn how to describe this in terms of the intervals where your graph might be increasing or decreasing. Next, we'll be naming maximums and minimums. So a minimum occurs whenever your graph changes from decreasing to increasing. So let's look at it on a graph. So here, if you look, my graph is going down, it's decreasing, and then all of a sudden it's increasing. So at that point where it changes, this is a minimum. And then let's look at maximum. So a maximum occurs when your graph changes from increasing to decreasing. So here, my graph is increasing, and then all of a sudden it changes to decreasing, which creates that little hill, which is a maximum. And then here, again, I'm decreasing and I change to increasing, so we have another minimum. So the minimums are just like the bottoms of a valley, the maximums are hills. Now, one thing to point out is that your maximum or your minimum is not always the absolute highest or the absolute lowest point on your graph. For example, here we're calling this a minimum even though our graph does go lower at some point. So that's why it's important to understand that we call it a maximum or minimum whenever that change between increasing and decreasing happens. So this would actually, since this is the absolute lowest point on our graph, we would actually call this an absolute minimum. And since these are not like the absolute highest or the absolute lowest, we would call these relative max and min. So now moving on to average rate of change. So the average rate of change between 2 points is the ratio of the change in y values or over the change in x values. So this might look really familiar to the warm-up. It's essentially the slope formula. So the average rate of change is essentially if you take the 2 points and you connect them with a straight line, it's the slope of that straight line. So notice that my original graph here is this parabola. It's curved. But if I'm finding the average rate of change between these 2 points, you connect it with the straight line. So it's an estimate rather than an exact, because this slope is always changing, the green slope, but this blue slope we can find. And again, this is called the average rate of change. Just think of it as using that slope formula. And last, these zeros. The zeros are where your graph crosses the x-axis. So notice here, we don't care about where it crosses the y-axis for this particular characteristic. It's where it crosses the x-axis, and then you list the x values where it crosses. So this graph has 2 zeros, one at -2 and one at 3. Okay, so here we have one big example that we're going to do together. We're going to be looking at this graph, and we're going to see if we can name all of those different things that we just talked about. So let's start with doing our maximums and our minimums. So remember, maximums occur when I change from increasing to decreasing. So I do have a maximum value here. This is a maximum. And for the maximum, you look at the y value because we want to know how high or low it is. So if I look over at the y value, maybe I'll draw a little dotted line over like this. We can see that we have a maximum at 3. And now I'm going from decreasing to increasing. So that gives us a minimum. So we see we have a minimum right here. Let's look at what that y value is. So you can trace it over. And that y value is -1. So that's a minimum. And if we keep looking here, I'm going from increasing to decreasing. So this is another maximum. And this maximum occurs at 2. So here we have 2 maximums and 1 minimum. Now let's name our zero. So remember, we're looking for the times when our graph is crossing the x-axis. So I see that we have a 0 here at -4, a 0 at -1, and 0 at 3, and a 0 at 5. So we have -4, 1, -1, 3, and 5. Okay, so now let's learn how to describe where our graph is increasing and decreasing. So first, I like to go in and mark with arrows to show whether it's increasing or decreasing. So remember, we always read our graph from left to right. So here I'm increasing, here I'm decreasing. Here I'm increasing, here I'm decreasing. So I'll actually highlight it this time so it's a little bit clearer. So green is where we're increasing, red is where we're decreasing. Green is where we're increasing. Red is where we're decreasing. And then let's also just add this into your graph. Let's make this assumption that we have little arrows at the end like this, implying that it continues in those directions forever. So how can we describe these different intervals? So we're going to describe them in terms of the x value. So let's start with the regions where it's increasing. So we want to first describe this region right here. So we can see that the x values that work for this region are everything -3 and to the left. So everything -3 to the left, our graph is going to be increasing. So our graph is increasing when x is less than or equal to -3, and that describes this region. Again, here's -3, and we want everything to the left, which is why we said less than, and we'll include that point, so or equal to. And now we need to include this region from here to here. So here we're starting at 1, and it keeps increasing until we get to 4. So we can describe that like this. 1 is less than or equal to x is less than or equal to 4. So this means between 1 and 4. So we've just described the two green regions for increasing. Now let's see if we can do the same for decreasing. So I see that we're decreasing from here to here, which on my x-axis is from -3 to 1. So that's our first region. So since it's bound on both sides, we can write it like this. So -3 is less than or equal to x is less than or equal to 1. So between -3 and 1. And then we also need to describe this region on the right. So this starts when x is 4, and it's going to continue everything to the right of that. So we can describe that as x is greater than or equal to 4. That will describe this region infinitely. So again, increasing and decreasing we describe in terms of intervals of x values. Okay, now let's see if we can find an average rate of change. So we need to find the average rate of change between x equals 1 and x equals 4. So let's see if we can find those two coordinates first. So when x equals 1, our y value is -1. So we have 1, -1. And when x is 4, our y value is 2. So 4, 2. So again, here they're essentially asking us to find the slope of the line that connects those 2 points on your graph. So right here. So again, on my actual graph, the slope is actually changing constantly because it's curved, but the average rate of change will be the slope of that straight line between the two. So we're going to use that slope formula. So we'll do y2 minus y1, so minus -1, over x2 minus x1. So this becomes 3, and this becomes 3. So the average rate of change is 1. You could also tell by looking at the graph, if we connected these two, the slope of this line is 1 over 1. Okay, now we're going to do a quick review of domain and range, which we have talked about in a previous lesson. So remember, the domain is all of the possible x values that work. So if you look, our graph is going to keep moving to the left forever. It will keep moving to the right forever. So our domain is all real numbers. Let's use interval notation. So let's do -infinity to +infinity. Our range, remember, is all of the y values that work. So for the y values, I see that we definitely have a high point. So that's here at 3. But our graph is actually going to continue decreasing infinitely because of the arrows on either side of our graph. So it's going to keep going down and down and down forever. So our y values that work are everything 3 and below. So our lower boundary for doing interval notation would be -infinity, and our upper boundary is right here at 3, and it is included. So I will do a bracket. And remember, we never include infinity, so we always do parentheses for those. And then last, let's see if we can describe the end behavior. So let's start by looking at the right side of our graph. So as we move towards the right, if I continue with that arrow, our graph is going down. So the way we describe that is as x approaches positive infinity, f of x approaches negative infinity. Again, as we move to the right, our graph is going down. Let's see what happens as we move to the left. So as we move to the left, if we kept going, our graph is also going down. So as x approaches negative infinity, meaning moving to the left, f of x approaches negative infinity. Again, meaning our graph moves down. So here we've described all of the major characteristics of this graph. So I know it's a lot of different stuff, but the more you practice it, the easier it gets. Okay, here is the last example for this video. So please pause the video and give this one a try, and let's make sure to add little arrows to the end of our graph as well. And we'll check your answers in just a few moments. All right, let's check. So we can see that we have a maximum here at -1 because it's a little hill. We have a minimum here at -4 at the bottom of our valley, and our only zero on this graph is here at -3. So here you can see that I've marked decreasing, increasing, decreasing. So our graph is increasing between -1 and 1, so in this region. So you can write it like this. And our graph is decreasing, it's red, everything to the left of -1, so when x is less than or equal to -1, and everything to the right of +1, when x is greater than or equal to +1. Then we were asked to find the average rate of change between x equals 3, which is this coordinate, and -3, and then when x is +3, which is this coordinate. So again, they're essentially asking us to find the slope of the line that connects those 2 points. So here's the slope formula, and you should end up with -1/2. Since we do have those arrows on the end of our graph, that means that our graph is going to continue to the right and to the left infinitely. So our domain is all real numbers, which we can write like this. Our graph is also going to be pointing down and up forever, so our range is also all real numbers. And then for the end behavior, moving to the right, our graph goes down. So as x approaches positive infinity, f of x approaches negative infinity. And then moving to the left, our graph goes up. So as x approaches negative infinity, f of x approaches positive infinity. All right, that is all for today's video. Thank you so much for watching.